So, our last talk of the Redshift and distant galaxies is going to be Dr. C.S. Unnikrishnan, who is also, as I think everyone who's spoken here, former podcast guest, but his accomplishments far eclipse appearing on the DemystifySci podcast, obviously. He is at the School of Quantum Technology, at the Defense Institute of Advanced Technology, and has been working on exploring the anomalies of physics. And so I cannot think of anyone who is more capable to walk us through the various difficulties the standard models are facing. So give it up to Dr. Unnikrishnan.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark. Before I go to the topic, I wanted to thank Hilo and Anastasia to give me the opportunity to come here and talk to you. What I want to do today is not a cosmologist's review of cosmology. I'm talking as a laboratory physicist who does experiments and look for evidence and the physical basis for cosmology today. And as I said, it's going to be a cautious review. And I will tell you what's the reason for this caution. Of course, we know that cosmology evolves. 100 years ago, we didn't have a proper cosmology theory. So observational sophistication is an important element in cosmology. As observations become more and more sophisticated, more and more accurate, elaborate, things change. We find new things. And there are some examples there. The CMBR fluctuations, return of the lambda, more recently. And the theoretical framework has enough margin to accommodate tensions. And you will see that there are a lot of tensions and which have been discussed here in great detail. Then what is more important is sustained criticisms by the most experienced cosmologists who contributed to our present model of cosmology. That could not match or dent the standard model sufficiently. The example I give is steady state. I mean, people like Fred Hoyle, Burbidge, Nallikar, and so on. 50 years of sustained criticism. They have contributed to the development of cosmology by their criticisms. And their calculations of elemental abundance and so on is very famous, and they are big contributions to cosmology. But finally, even their students didn't take them seriously enough. As I know, because I was in the TATA Institute 40 years, where Nallikar worked for several years. Now, we have several cosmological invariants, which we know from 1932, which were established. And they have sort of remained. Whatever observations, theories which came later, these invariants have been there. You cannot deny them. Redshifts, well-thermalized radiation background, nearly flat geometry. These are facts. Now, if you look at this book, which was written by Hoyle, Burbidge, and Nallikar, you will see this contained a very powerful criticism of the lambda CDM model. It's a very well-studied criticism, but even that could not alter the whole model. I mean, tensions are there, but there is no refutation. There's a big difference between the two. Nallikar passed away last month, so I just wanted to mention here. But these are the kind of cosmologists who have been criticizing not just people who don't like Big Bang. These are people who developed our cosmology. Now, in their book, this picture is there to show how the crowd follows the leaders. Okay, it is from their book. But also you can see at the end of it, there are some people some geese walking backwards. So some of those people are probably here, but uh, now when we look at progress of science, of course, the standard thing of advancing a hypothesis, antithesis, then the synthesis comes from experiments, sometimes thought experiments, but real experiments are more important. So experimental tests, they are very few. There is one universe and we have to observe all this. But our observations, when we look at faraway distances, is also going into the past. So it's a very strange kind of a system which we are trying to observe as a physical system, evolving physical system. Now the question is, what are the crucial observations we can do? And what are the falsifiable predictions, refutable predictions? See, there is a big difference between refutation and validation. So we are on the path of validation quite a bit in the standard cosmology. But real refutation means there has to be a prediction. For example, just as an example, right now it is nearly impossible to get an age of the universe much more than 15 billion years. So if there are galaxy clusters found at 25 billion years kind of redshift, then one could consider it as a refutation. But that is not the case today. We have tensions, but nothing refuting is of Indian. And there is a old philosophical Indian method of saying not this, neti. In the sense, it's a very tedious way of trying to refute something. You look at one by one and say, not this. Then the rest you can look at. But this obviously is very tedious because each one you have to negate. But I may have to refer to that kind of a method here in cosmology. In physics, we try to do direct experiments, but cosmology, this method is also a reliable method. So I want to critically examine some important aspects of modern cosmology in the spirit of this negation method. Now, facts from elementary cosmology. An expanding universe with the approximate homogeneity and isotropy, one of the large spatial scales, is the most popular physical model of the universe today. Observations of oldest stars and galaxies require that the age of the universe is larger than about 14 billion years old. Various observations suggest that the spatial geometry of our universe is approximately flat, Euclidean. So if two light rays are going parallel, they keep going parallel. And in any case, with the radius of curvature, even if it is curved, it is much larger than 10 to the 26 meters. The underlying physical theories are general theory of relativity and the standard model of particle physics. Then the minimal facts require that we require a nearly singular origin, that is infinite density of matter energy of the universe at a finite time in the past. And at an early stage, exponential expansion called inflation today, due to an unknown agent and mechanism that we don't understand it. Also, the Euclidean nature cannot be explained with neither the observed amount of baryonic matter, particles known in standard model of particle physics, nor the estimated amount of baryonic matter. So this is so therefore we need undetected matter must be present and dominates 90% of that. It's that kind of. So if you say, okay, we have standard theory of general relativity, particle physics, but what goes as ingredients of the model of universe is much more beyond these two theories. Current observations require an asset unobserved dark energy dominated by a component with the unusual equation of state P equal to minus rho. We really don't know how to get it from elementary particle physics except by hypothesizing something very convoluted. So this is a lambda CDM model, which all of you know. Now, the essential consistency with the empirical experience, Hubble law is the first one. Observed redshift and its relation with the deduced distances. Redshifts are accurately observed, but distances are deduced by various secondary methods, and there is some uncertainty. Then there's a thermal radiation at a particular temperature with a well-characterized energy density. Reliable spectroscopic evidence that the temperature of the radiation in the past has been systematically higher. I will show some data. Then fluctuations, angular correlations, all that were talked about here. Then the approximate abundances of light elements, hydrogen, deuterium, helium, lithium. These are also part of our standard cosmology. Then what is important is the homogeneity and isotropy of the universe. I have more to talk about that, or the cosmological principle. But whatever it is, we have to face this problem in the current model where we say the spatial geometry is flat. Then the only possible universe is an infinite universe or a near infinite universe at all times, in the beginning and in the future and today. It has to be infinite universe. So the problem of infinite density or near infinite density, near infinite temperature and near infinite volume, we have to face at some time in the past in this kind of a universe. It is not a finite universe at any time. If you accept that it is strictly Euclidean, flat geometry. So we have to face all these strange things about our model of the universe. Now, there's an old, when you say cosmological principles of homogeneity and isotropy, this was first proved by E.A. Milne in his model of the universe, which was very different from the standard Big Bang model, where he considered a finite universe exploding and expanding with all velocities from 0 to velocity of light. So he said, if you have such a system, random position, random velocities, but so small, it could be the size of an egg, size of a Earth, whatever, small size compared to the size of the present universe, then it expands and becomes a universe like that. Then he said, though the initial primordial universe is not isotropic and homogeneous and so on, all that history will be forgotten. Once it expands, of course, Hubble law follows trivially because the fastest object reaches the farthest and is linear. So you get the Hubble law very easily in that. Not only that, he proved that because of simple vectorial nature of the velocity, if you take the particles in that, wherever you, not at the center, wherever you are, it will be locally isotropic and locally homogeneous. This is a remarkable proof by Milne. You can look up. There's a review by Professor Chandrasekhar where he has explained this. You need both this vectorial nature as well as special relativity. So in Milne's model, there is no general relativity or gravity. It is just purely explosion from a finite volume going up to the present size with all velocities from 0 to c, only special relativity. Okay. So I don't want to go into detail, but you can check this. So Milne was the originator of this cosmological principle. Now, let's look at this cosmological principle because there is actually a lot of confusion about it. What is the cosmological principle really? Because we think that the universe, even at large scale, is not really homogeneous and isotropic. This question was raised here. However, what is relevant for the gravitational dynamics of our universe is a homogeneity and the isotropy of the gravitational potentials, not matter. not the homogeneity and isotropy of matter distribution. Let me try to explain this slightly better. I think it's a serious misunderstanding, unfortunate misunderstanding of the cosmological principle. The crude statement of the cosmological principle, which is a basis of our cosmology today, using a FRW metric and so on, the universe is homogeneous and isotropic at very large scale. This is a crude statement. It is necessary, this statement is necessary to assume the Friedman, Lemaitre, Robertson, Walker metric. Then general relativity gives you the solutions. But obviously this is factually incorrect. Even at gigaparsec scale, it is not homogeneous and isotropic. We know that. In fact, there's a recent paper which was also mentioned here. Is observable universe consistent with cosmological principle? And they conclude that it is not really. However, we are talking about gravitational physics, not material science. The rigorous statement of the cosmological principle is very different. The gravitational properties of the universe is homogeneous and isotropic at very large scales. This can be proved. In fact, it is factually correct to a precision of 1 part in 10 to the 8. Certainly 1 part in 10 to the 6, 1 part in a million. Why? If you look at Earth's gravitational potential in this room and take the ratio with the average gravitational potential of the entire matter in the universe, it is 1 part in 10 to the 9. It's a small, Earth is nothing. Earth is an inhomogeneous speck, but gravitationally it doesn't count. Similarly, galactic gravitational potential in intergalactic space to average gravitational potential of the whole matter in the universe is less than 1 part in a million. And that's all what is relevant for general relativistic expansion of the universe, not matter distribution, gravitational potentials, metric. So this paper, for example, says that yet since a cosmological principle is not a fundamental physical symmetry, but rather an assumption imposed when we interpret observations, there is nothing that prevents it being violated at higher precision, like few percent. That is not correct. It's a wrong statement. In fact, tomorrow I have a talk where I will prove that cosmological principle is related to a very fundamental symmetry, which is the principle of relativity, very surprisingly. So this conclusion in this paper is incorrect, that if one is content to do cosmology at the 10% level, FLW metric may be a valid approximation. Depending on how the anomalies of this in this review are resolved, limitations of this metric will either be evident or it may be possible to reconcile with the precision cosmology program and so on. At a person level, I'm saying, it is a 1 part in million level, it is homogeneous and isotropic at large scales. And therefore, we know that we can write this metric in various forms, but there is no need to go into the exact form of that. But one aspect I want to point out in this, as soon as we say that we have a universe which is homogeneous and isotropic, and there is a metric, mathematical description of that available, this is a metric with an absolute time and absolute space. Okay? Because that dt is a single time all over the universe. Anywhere you are, it is synchronized. In fact, practically you can take the temperature of the microwave background as the universal time in case if you want a physical clock. Also, it has absolute space. And you see there, it is not dt square, it's c square dt square. Today there was some discussion here about variable light and so on. In general relativity, as it is practiced by everybody, cosmologists, astrophysicists, physicists, C is variable with gravitational potential today. In fact, there is a lecture by Thibaut Damour, who is an expert relativist. You can see it in the YouTube, where he describes Einstein's discoveries purely in terms of that G00 factor, C square dt square. How he made variable and constructed general relativity. In fact, we keep measuring the variable speed of light in what is today called Shapiro delay. So all that is part of general relativity. We have not forgotten any of this. Einstein didn't forget it. Other people didn't forget it. Today's general relativists know that light speed is variable in a gravitational potential and it's routinely measured in experiments. Now, because of this absolute nature of time and space, the universe itself is not Lorentz invariant. If you are in a frame which is moving, you see a different universe with a dipole anisotropy. This was specifically stated by Hermann Bondi many decades ago. The thing is, all physical processes happen within this universe. Okay, all our activities, all physical processes happen in this universe with that absolute time and absolute space. Yet, our local physics, we say it is Lorentz invariant. There's an inconsistency there, which I will talk about today, I will talk about tomorrow, not today. So all gravitational processes obeying Einstein's equations happen within this absolute space and its absolute time, though Einstein's equation itself is formulated with general coordinate invariance, which is an extension of Lorentz invariance. This happened because of a historical aberration. Einstein's theory happened before cosmology was known. If cosmology was known, the absolute space was known, absolute time was known, before Einstein formulated his general relativity, he would not have chosen general coordinate invariance. He would have chosen the Mach's principle as a basis. But this aberration happened. So the correct Einstein's equation should have been this, where the TIK, energy moment tensor, plus another TIK of the matter in the universe permanently in Einstein's equation. Today, that is not the case. This is not today's Einstein's equation. It is this. And this is actually incomplete. It should have been this. Again, this is a topic for tomorrow. In fact, many of these things are discussed in my two books, which was published 2 years ago, especially the second one. So there you will see that cosmological principle is indeed related to a fundamental symmetry, that of principle of relativity. So it's a very robust basis for our cosmology. Now, I just want to review some observations. Standard lambda CDM, cosmology predicts a linear increase of the temperature of the microwave background with redshift. It's a very important observation when we consider models of redshift CMBR. This is from one of the papers looking at water absorption in quasars lines. You can see that as you increase in the redshift, the temperature of the microwave background increases from 3 degree, 2.7 degree Kelvin, all the way to 20 degrees. Okay? Molecular lines, absorption lines show that if you look at faraway molecular systems, there the actual temperature, which is a temperature in the past, temperature of the microwave background in the past, is higher. There is clear evidence for that. This is another from CO, CN, and various molecular lines like that. You can see it follows roughly the linear relation which is required, because this you extend to 1100, you get that 3000, 4000 degree at the recombination. Now, these are some of these people are my colleagues in TATA Institute, Sri Anand and so on. So there are very good measurements of the fact that the temperature of the microwave background in the past at some Z is linearly related to the redshift itself. So this cannot be denied when you talk about models of CMBR and redshift. Then abundance of light elements, I don't want to talk much because people know much better than me here, except to mention that deuterium, which was talked about here, is a reasonable evidence for the standard Big Bang kind of a scenario, especially as I mentioned yesterday, Hoyle very specifically mentioned that it is possible to get all this in stars, but we need much more time, maybe 10 to the 11 years, which is right now not you cannot accommodate it in the standard model of cosmology. Now, this is just a Hubble relation which is getting plotted, redshift as a function of distance or vice versa. And you know this now, there are much larger surveys. Indra will talk about gaps. Those gaps are getting filled up and so on. And if you look at the fits there, of course, still the lambda CDM with a cosmological constant is most favored. But even an empty universe, something like the Milne universe with a finite amount of matter, which is just freely coasting in this universe, is not a bad fit. Just a linear coasting. It is slightly different. Things can change in future. And of course, one is today when we talk about standard cosmology, we are talking about various observations together. We have to explain all this together. And that's very important. One cannot take one aspect and then try to say make a model of the universe. This is why, again, I want to stress the importance of refutation and the versus constructing an alternative model. Refutation is much easier. You have to just refute whatever model you have. You are not obliged to provide an alternative model. That's a different exercise, completely independent. It may be possible, it may not be possible. But refuting something, if you go to the fundamental physics reasons, there is a chance that the present cosmology may get refuted. Sometimes it may take decades, centuries, I don't know. But the point is that supernova data and the CMB data more or less orthogonally contributes, and both had to be explained in any model of cosmology. This I show this a dark energy survey. 300 million galaxies are being imaged. I show this not to discuss this data. I want to show this for the purpose of showing the beauty of data, beauty of large data. And this is not private data. Everybody has access to this data. Thousands of supernovae. Anybody can analyze. So what I'm saying is, present style of doing astronomy and cosmology, data is open, it's accessible to everybody. And if you are serious about deciding whether present cosmology is one or we have to necessarily go for another model, possibility of refuting something definitively should be in all this data, which is accessible to every one of us. So in the dark energy survey, the number of supernovae is extended, gaps are getting closed, and I just want to mention whatever they say in their publication. It's not my statement. It says 25 years ago, they found that this at 3 sigma level, evidence for an accelerating universe. Importantly, they noted that since the deceleration parameter is measured at the present day, the data span, a wide range of redshifts, Q0 can only be measured within the context of a model. So you need a model to do this fits. Okay. Doing the same, that is, with a model, you fit the data. This dark energy survey, which surveys millions of galaxies and thousands of supernovae, it says in 5-year data, gives that kind of confidence level. You can see phi sigma, that universe is accelerating. And there's only a 10 minus 7 chance that the expansion of the universe is not accelerating. Okay, that is their statement. That's an official statement of this thing. But from various discussions here, we know that this is all model dependent, and we should. Now, I want to look at this redshift physical mechanisms for a moment. Of course, you can have, in the earlier days, we thought it's a special relativistic redshift, Doppler shift, because galaxies are receding. Then people said, no, it's expansion of space itself, and everything co-stretches, including wavelengths and so on, as if wavelength is a physical object embedded in space. Space expands, wavelength expands. Okay, possible. There's another possibility. The gravitational potential of this in this room could be steadily decreasing or increasing, whichever way, and you can get a redshift even from that. Today morning we saw an example of that. Point I wanted to make here, the second Friedman equation, which is describing the acceleration or deceleration, is actually at least in its neo-Newtonian interpretation. That is Newtonian physics with relativistic E equal to mc square added to it. It is suspect. In the sense, I want to just point out this fact here. We know that in the standard general relativistic Friedman universe, we try to do the theory and we can derive an equation for the change in the energy density. From the Einstein's equation, we can do that. And it gives that following form: energy density epsilon, P is a pressure, A is a scale factor, A dot is its change, velocity. And then we assume an equation of state, P equal to WE. For matter, it is W is 0, radiation it is 1/3, and so on and so forth. And from that, we derive an equation, epsilon, the time variation of the energy density in the universe, and that is given by that equation. For pressureless matter, energy density changes as 1 by A cube. Of course, universe is expanding, volume is increasing, energy density decreases. Radiation, it is 1 by A to the 4. So this is all derived from assuming a pressure for the radiation. However, when we talk about this 1 by A to the 4 in the photon picture, we make a completely different physical statement. We say 1 by A cube from the number density of photons, and 1 by A comes from the redshift of the photons, the energy reduction. We derive the equation using a pressure in the first place, getting 1 by A to the 4, but in the particle photon interpretation, it's a completely different physical interpretation. These are not the same interpretations. If you also include now the pressure, which is momentum, change in momentum, there is another factor of A will come. So what I'm saying is, even in the theory of general relativity theory of the evolving universe, I don't believe that everything is correctly done. This is what we do now, but these things can be looked at again. That's a foundational part of cosmology, is not something which is fixed. So cosmological redshift, right now it is a belief that space is expanding, everything is taken. So I want to point out one thing here. Of course, this process doesn't conserve energy or momentum. Space expanding, energy violation is there. If that is the reason for redshift. If there is true recession, Doppler shift is an energy conserving process, but space expanding and redshift happening violates energy conservation. This is known. If you look at the writings of Harrison, this is very clearly stated. So there are other possibilities, which, as I mentioned already, it could be a gravitational redshift. It could be simple special relativistic Doppler shift also. So usually a cosmologist, when asked whether the Sun-Earth distance or the Earth-Moon distance changes due to the cosmic expansion, because space itself is expanding, it could stretch everything with it, because even a wavelength is getting stretched somehow by space. Normal answer is it doesn't, citing the gravitational binding between such systems as the reason. The reason. But is it the binding energy? Is it the gravitational binding energy or the gravitational force? We don't know. So let's estimate. What's the binding energy between Earth and Sun, Earth and Moon? You can calculate those numbers. GMM by R, GMM by R square. So that some numbers are there. Binding energy between Sun and Earth, all that can be calculated. Now, all we can also calculate between galaxy and galaxy, 10 kiloparsec size, separated by a few megaparsec. They are actually larger numbers. The binding energy is much larger. So we are saying galaxies can overcome this binding energy by the expansion of space, but not Earth-Moon distance. There is a certain physical inconsistency in this statement. People don't calculate these numbers. Of course, if you talk about the gravitational force, this is a possibility because matter is more isotropic, homogeneous. Therefore, really there is no force between a galaxy and galaxy because each galaxy is pulled from all sides. So you have to make further statement. You cannot just get away with the statement that gravitationally bound systems don't expand with the expanding space of the universe. It has to be more, it has to be theoretically established, and it is not done yet. And as you know, if you look at the data between Earth and Moon, the distance is changing, it is increasing. Part of it can be explained by saying that there is tidal dissipation, but part of it remains unexplained even today. Okay, I'm not taking a side, I'm just stating a fact. Okay, now the question of tidal light. I want to make a statement about this because I'm a physicist and I am tempted to make this statement. Of course, there is no mechanism for the energy dissipation. The tidal light model is never specified. Some scattering process, maybe gravity, something else is what is said. And the usual proof against this is discussed here, the light curves of the supernova, for distant supernova, which was discussed here. I want to give another proof.
About 10 minutes over already.
Suppose there's a scattering process. If there is a scattering process, whatever it is, that is amounts to a refractive index, some kind of a refractive index. To avoid excessive loss of intensity, that refractive index must be real. There's no, okay, that like a transparent medium. And now there are two effects. One is gradual loss of energy, which is a redshift. But it will also have a time delay because effective refractive index means the speed of light will be different. Now, suppose that delta f by f fractional change is of the order of delta t by t, the delay. I'm not saying that it has to be that way. Then it's already ruled out because the scattering mechanism that could be invoked for light is not applicable for the scattering of gravitational waves, which are thousands of kilometers wavelength. Now we have at least one, actually more, evidence of binary neutron star merger from which gamma rays as well as gravitational waves arrive simultaneously on Earth with hardly more than less than 10-second delay, if at all. So therefore, and that is coming from a redshift of 0.01, which is 10 to the 23 meters. So it takes 10 to the 15 seconds to reach. And if you have a 1% corresponding to that redshift delay, it cannot be accommodated because of maximum delay is only 10 seconds. Whereas if the delta f by f is of the order of delta t by t, delay would be enormous. So what I'm saying is the tired light kind of mechanisms can be ruled out just by looking at how gravitational waves and gamma rays come together within a model, whatever model. So if you tell me what is your model of tired light, I can bet that I will be able to rule it out using this kind of observations. So this I will skip in the interest of time, but it was to state that there is a talk of needing something like quantum vacuum to explain a cosmological constant, Casimir force and various things. I don't want to talk about it here, but I just want to show you a reference here where I analyze this question and conclude that this is not the way to generate a cosmological constant, but I don't want to talk about it here. Finally, 2 minutes on this. So far, nobody discussed modified Newtonian gravity here. As you know, it is an idea where you change the law of gravitational attraction from Em by r square to a 1 by r kind of a force. Earlier, Anastasia was talking about a planar model of the galaxy. If you have a plain 2D, strictly 2D system, the potential is logarithmic, and then you can get a 1 by r force. Maybe that's what she was doing. But here it's a different idea. But once you have that kind of a modification, then you can show that the v square is distance independent of r. It is of the form square root of g m. And it is very successful in trying to model flat rotation curves, as you know. However, the same idea is also applied. The present strong proof of modified Newtonian gravity, one in galaxies, for example, is quoted as what is called Tully-Fisher relation. And we know that for several decades, we know that there's a relation between the rotation of stars inside the galaxy, which is well within the galaxy, the fourth power of that, and the total luminosity. And that is related to mass. So there's v to the 4, power of 4 is proportional to gm. That we know already. And this is highlighted as a proof of modified Newtonian gravity because you see the last equation v square, since it is not a function of distances, and you get this Tully-Fisher relation automatically from MOND. However, there is a complete logical flaw in this argument of presenting the Tully-Fisher relation as a proof for MOND, because the Tully-Fisher relation is always determined well inside the galaxy. It has nothing to do with the region outside the galaxy. It is inside the galaxy. The relation is completely determined. Even if you know nothing outside the boundary of galaxy, the Tully-Fisher relation is established within that. Whereas the modified Newtonian gravity is relevant only when far away from galaxies where So what I'm saying is, for most of the galaxies, we know that the Tully-Fisher relation is valid where MOND is not even applicable. So I just wanted to make the statement that MOND is unlikely to solve any problems of cosmology. And so I conclude. Question is there a crisis in cosmology? There are enough observational indications to think that the current standard picture will change to some extent, maybe large extent. There are certainly several conceptual gaps that will find a different foundation than lambda CDM. I don't personally, if you ask me, I don't believe lambda will stay. better physical explanation. But again, I stress, refutation is different from providing an alternate cosmology. These are, if we treat, these two are completely different. We are not obliged to give an alternate cosmology. What is a more fruitful exercise is to analyze the current data and look for a refutation of any of these elements. Thank you very much.
All right, Alexander. Always first.
Sorry. Yeah, I will be short.
Alexander the Great.
Came to India, right?
Just about. We were shocked.
Yeah, you were mentioning tired light, and I agree so far. You need to be quantitative. It's not enough to say, oh, it could be something. Dick's theory, you mentioned that delta F over F is equal to delta T over T. It's the minus missing here, because the frequencies are decreasing, so the timescales are increasing. Yeah. However, it's completely consistent with what Dick said. It's a necessary consequence of Dick. That being said, you're right that it contradicts gravitational waves. And
if that is a model, we can always
hard to digest, maybe. But I think we should shift that to the panel. But I'm really grateful that you're here as a member of the collaboration also.
Yes.
And I'm curious to.
But I have not talked about this there.
To ask some questions.
We don't discuss tired light in LIGO collaboration.
Okay.
Things we don't talk about.
Thank you for a very detailed talk. At one point, you had mentioned the radius of curvature must be greater than about 10 to the 26 meters, basically the radius of the observable universe. Is there a minimum magnitude in order to have that curvature?
No, this is what we observe is this. So the universe could be infinite, but it need not be infinite. We don't know. The point is, when we say we have a k equal to 0 spatially flat universe, that's an approximate statement. If it is very big, say let's say 100 times 10 to the 26,
right,
we would think that it is flat. Maybe it is not flat. It could be curved at that level.
Is there generally, basically, if we were to have like a spherical universe, hypothetically, is there a general, like, how many more magnitudes would we need? Is that something people look at?
For example, if you look at the first model of the universe constructed by Einstein, it was a spherical universe with about this kind of properties. Matter closing the universe, just closing it. And in fact, the relation between G and the total mass of the M, everything was done already by Einstein at that time. But of course, he had a cosmological constant to balance it so that it's not expanding or contracting. But essentially, the point is, if you have that kind of mass, critical density, if the density is more than that, it will be closed. It will be closed universe without any boundary. In the sense, it is general relativistically closed. Okay. So if you move in that universe, you will come back to the same point if you travel sufficiently long time.
Kind of like the game of Astro.
Yeah, so there is no boundary, but right now we think that is not the situation. It is probably a truly flat universe. But if it's a truly flat universe, it has to be infinite, not only today, in the infinite past as well. It can only start as an infinite universe and end as an infinite universe. Infinity cannot be reduced to anything.
Cool. Thank you.
So thank you for the wonderful talk. Can you go back to the slide with the temperature of the CMB as a function of redshift? Oh, sorry.
This will do, or
yeah, we can start here. So we've been talking about proper motion expansion versus the stretching of space. I just wanted to point out that we may have a possibility of a test here, because if you actually have proper motion expansion, then kinematics effects are going to matter, and then the Lorentz contraction is going to create a slightly higher energy density at higher redshifts, and then you're going to have a slight departure from this linear profile. So we published a paper in 2024 showing this, and you can see here just this this chart here that you already have some little deviation, and you're going up the linear profile here, which would be the expectation if you have a proper expansion. And if you go back one slide,
I sort of understand what you're saying. If there's actually moving, there's contraction effects and energy density. So maybe possible.
And then if you go in and if you see here at higher redshift, you see it's a pretty big yellow bar, so we need better data, of course. But the expectation linear relation would be the yellow one, and you can see also here that most data lie above this line. So with better data, more precision data, that could be a test.
In fact, I would like that. If you ask me for personal beliefs, see, belief is not a bad thing when we talk about cosmology. Belief is a bad thing in physics, I think. But cosmology is between physics and theology or something. Belief is okay. My personal belief would be still standard, proper motion, relativistic Doppler shift. But the majority thinks that space is expanding, and that's fine. So you're right. If this data becomes much more precise, one will be able to settle these issues. Thank you.
Thank you.
So I think there's a flaw in your argument that the data rules out tired light. Because you're making an implicit assumption that gravitons are not affected.
No, not that. I'm saying gravitons are not affected the same way, because it is gravitational, gravity acting on gravitational thing and gravity acting on light could be different. The wavelengths are very, very different.
Right, so you've ruled out any model in which photons and gravitons are affected significantly differently, but if they were affected the same... Then...
Exact. I know. Then my argument doesn't work. True.
Right.
True.
Okay.
Yes. So that's why it said a mechanism should be spelled out.
Awesome. Yeah, thank you so much.